In this video, we are going to talk about friction forces. When an object is in motion on a surface, there is always a resistance to the motion because the object interacts with the surface. Imagine yourself while trying to drag a massive table on a rug. Probably we all have experienced such a struggle. When you first apply the force on the table, it resists to move. But after a certain amount of force, that resistance breaks. Even after the motion started, we should continue applying force to the table in order to keep the table in motion. This resistance of the table to dragging is a result of the friction forces between the table and the rug. The resistance preventing the table from the move and the resistance that we need to overcome in order to keep the table in the motion. The first one, the one that is preventing the table from the motion initially, is called static friction, and the one that we need to overcome during the motion is called dynamic friction. Let's see how friction force changes with the applied force. In the static region, the friction force that prevents the object from moving increases linearly with the applied force. To calculate the value of the static friction force, let's recall the third law of motion. For every action, there is an equal and opposite reaction. Therefore, in the static region, the magnitude of the friction force is always equal to the force applied. And as we saw in the table example, after a certain amount of force, the object breaks free and starts to move, and this region is called the dynamic region. In the dynamic region, the friction force still exists, but the magnitude of the friction force drops to a certain level. The magnitude of the friction force just before the object starts to move is called the maximum static friction force. So let's talk about how do we calculate the values of those friction forces. From experiments, we know that both the maximum friction force and the kinetic friction force are proportional to the magnitude of the normal force exerted on an object by the surface. To define that proportionality, we have two different friction coefficients. Mu sub s, coefficient of static friction, and mu sub k, coefficient of kinetic friction. With the help of those friction coefficients, we can define the friction forces in terms of the normal force. Let's talk about some properties of the friction coefficients. The values of mu sub k and mu sub s depend on the nature of the surfaces. The direction of the friction force is parallel to the surface with which the object is in contact and opposite to the actual motion. Here are some numerical examples of static and kinetic friction factors. Let's take a look at a quick and common example on experimental determination of. In the example, a block with a mass of m is standing still on an inclined surface. The incline angle is increased until the block starts to move. And we are going to show that we can obtain static friction coefficient by measuring the critical angle, theta, at which this slipping just occurs. And to analyze this problem, let's position our coordinate system as shown in the figure. After defining the coordinate system, we can write our force balance equations. In the x direction, we have two components. First one is coming from the mass of the block, m times g times sine theta. And the second one is the friction force we are looking for. And in the vertical direction, in the y direction, you have another two components. First one is the normal force, and the second one is the m times g times cosine theta. Since initially there is no motion on the system, both of the equations must be equal to 0. At this point, it will be wise to indicate the positive direction for each component. For x-axis, we assume that this direction is positive, and for y-axis, we assume that this direction is positive. If we rearrange the equation number 2, we obtain m times g as shown. And then if we substitute this term into equation number 1, we can obtain the equation 1 as shown. And then making the trigonometric conversion and the arrangements, we obtain the friction force as this. Do not forget, we are looking for the friction force just before the block starts to move. Therefore, this friction force is actually the maximum friction force can be applied by the surface to the object just before the motion of the object starts. And the angle at that moment was given with theta sub c, the critical angle. So if we use the friction factor, the static friction factor, to define static friction force, we obtain F sub s as static friction coefficient times the normal force. And at the right hand side of the equation, we have n times tangent theta. But this time, I'm going to write theta sub c instead of theta to designate that this angle is the critical angle. Ends will cancel out, and here we obtain the static friction factor as mu sub s is equal to tangent theta critical. So these were the basics of friction force analysis.